Okay, guys, good evening. Let's,
Good evening, sir.
good evening.
Good evening, sir.
Let's get started. So by yesterday's lecture, we finished the first three chapters, that is solution to system of linear equations, solution to system of nonlinear equations, and basics of the finite difference method. Okay, now we are entering the fourth chapter. So this is the penultimate chapter. So this is solution to ordinary differential equations. Solution to ordinary differential equations. Or ODEs. Okay. You might have come across several ODEs in your studies, academics, or in your work. Can you tell a few examples where ODEs are encountered, or where application areas where ODEs are encountered? So routinely in solving fluid flow and heat transfer problems, we encounter ordinary differential equations. Okay. And in solving chemical reactions, we see ordinary differential equations. Okay. And let us say in solving population balance kind of models, population balance or predator prey models, etc. Okay. We also see ordinary differential equations in several other areas. For example, in the vibration of a string, or loading of a beam, or elastic deformation of a beam under a load. Okay. And many other examples. So, or even, for example, if you take electrical engineering, you have the RLC, the resistance, capacitance, and inductance circuit. So this is governed through an ordinary differential equation, and many other examples. Okay, so these are all areas where you will come across ODEs. So in general, we can write an ordinary differential equation that is nth order accurate, whether it is linear or nonlinear, can be represented using some function f, whether this could be linear or nonlinear, as a function of x, y, dy dx, d square y by dx square, d cube y by dx cube, and so on, e to the power n y by dx to the power n. Okay, so we said this is nth order, so that means this is the derivatives are up to nth order equal to 0. Okay, so where we realize that this particular f can involve either it is a linear function or a nonlinear function. Okay, fine. So in this, x is the independent variable. And y is your dependent variable. Okay. And as you recall, as you see here, you only have derivatives with respect to only one independent variable. That's why these are all ordinary differentiations, right? You just have d by dx and higher derivatives, right? And so on. So historically, it was actually although it appears that ordinary differential equations are much more simple when compared to partial differential equations, because partial differential equations, the number of independent variables are more, right? You may have independent variables such as x, y, z, t, etc. Many independent variables. As a result, we express the derivatives as partial by partial x of something, partial by partial t of something, and so on, right? So, but whereas in ordinary differential equation, you only have one independent variable, either we call it either x, or sometimes we call it with t. Okay, so you have only one independent variable, and that basically makes them somewhat simpler to look. But however, if you look at historically, people were able to numerically solve PDEs much earlier than they were able to solve some certain class of ODEs. Okay, certain class of ODEs which are kind of difficult to solve. So only after a while, once they essentially they were able to solve the ODEs after essentially solution methods for several PDs were kind of invented and applied. Okay, so that is, I think that is something historical note. Okay, now we have seen what is an ODE. Of course, we said either it is a linear or non-linear. Now let me write down here a few examples of ODEs, and then you can help me tell whether these are linear ODEs or non-linear ODEs. Okay. So in the context of algebraic equations, we already have seen what is a non-linear algebraic equation, what is a linear system, what is a nonlinear system in the context of algebraic equations. But what is it in the context of ordinary differential equations? These are now differential equations. So, so in the context of algebraic equations, we said if you have ax plus by plus cz, etc., equals some d, this is basically a linear equation because it's multiplied with a, b, c constants. Whereas when we have something like x square plus y square equals 1, we said this is basically a nonlinear equation because there is the x and y are raised to the power 1. Okay, so those are but those were algebraic equations. Right now we are dealing with differential equations. Right now we are dealing with differential equations or ordinary differential equations to be specific. Differential equation. So let me write down a few examples. The first one is let us say dy dx equals x plus y. Okay, second one is let us say dy by dx equals x square plus y. Third one is dy by dx equals x square plus y square. Fourth one is let us say dy by dt equals sine of t. Fifth one is let us say d square y by dx square equals y minus x. Sixth one is d square y by dx square equals e to the power minus y plus x square. Okay, so let us see which one of these are actually linear and which one of these are non-linear. Which of these are linear, which are non-linear? Can any one of you or some of you try to identify and tell me which ones we can call them as linear and which ones as non-linear? And if we call some equation as nonlinear, why we will call them as nonlinear? What is the rationale behind that? Can we identify which are the linear differential equations in this? Are all of them linear or some of them nonlinear? Let me also maybe modify something here. Okay, let me also make sixth one as y times d square y by dx square. Okay, yeah, okay. Can anybody help? Can you take a guess here? Which ones would be linear? Which are linear ODEs here?
X plus y, X square.
Seems
First one is linear or non-linear?
Linear, sir.
Linear. Okay. So okay. What is the rationale? What principle would you use to say whether it is linear or non-linear?
It's a line equation.
Equation of line. Okay. Okay. What about the second one?
Third one will be circle equation. Second one.
It's not really circle equation because you have dy by dx as such, right? Okay. I mean, if it is circle, you'll have x square plus y square equals constant, isn't it? But this slope need not be constant. Okay.
Yes,
So yeah. So what would be the second equation? Is it linear or non-linear? So I will tell the kind of rationale. Okay, then you can again guess. So if if something is a linear equation in a differential equation, then we will have the products of the uh, dependent variables. Okay, products of dependent variables show up. So if we have, we call something as a nonlinear ODE if there are, if the dependent variable appears as a dependent variable or its derivatives. Okay, appear as products. Okay, that means if the dependent variable is either multiplied with itself or it is multiplied with its derivatives and so on, then that means what we have is we are trying to solve for. So we are trying to solve for what is the distribution of y here, right? We're trying to solve for y, and then y itself is unknown, and then if you have products of those unknowns or its derivatives, right, appearing as certain terms, then we call that as a nonlinear term inside, and we call the equation as a nonlinear ordinary differential equation. Similarly, if the dependent variable uh, is made to go to higher powers, okay, or if it appears in exponentials or any transcendental functions such as trigonometric functions, sines or cosines, etc., where if the dependent variable comes or in any of these things, then also we can call it as a nonlinear ordinary differential equation because these are all nonlinear operators. Okay, so now with this as the basis, can one of you guess what would be which are linear? The first one is linear, okay, because the slope equals x plus y. There is no product of dependent variable with itself or its derivative. So dy dx is multiplied with 1, y is multiplied with 1. So this is linear. Okay. What about the second equation? Second equation, is it linear or non-linear? Second equation, do you call it as a linear or non-linear? It's okay if it is incorrect, you know. It's not
Linear, sir.
It's linear. It's linear because the dependent variables are not only the independent variable is raised. So this is it is still linear. What about the third equation?
Linear.
This is not linear. Why? Why is it? It is not linear. It is non-linear because you have y square term, right? So this is nonlinear because dependent variable is what you are trying to calculate. You are multiplying y with itself. So this is a nonlinear ordinary differential equation. Okay. What about the fourth equation?
Linear.
This is linear because you have dy by dt equals sine of t. So that's why it is linear. But if we had equal sine of y, this would have been nonlinear because then we are essentially making our dependent variable as the trigonometric function. Oh, excuse me, I'm in a class. Yeah, yeah. Talk to you, sir. Yeah. So if you are so if you have raised y sine of y, then it would be a nonlinear equation. Okay. So what about the fifth equation? Is it linear or nonlinear?
Non-linear, sir.
Nonlinear. Why? Why is it nonlinear? Okay, so we
Um,
have d square. Yeah.
yeah, order is 2.
No, order is 2, but still this is still linear, right? I mean, because you don't have a product of y with itself, so this is still linear. If the equation would have been so you're taking second derivative of y, but that doesn't mean that it is nonlinear as such. It's just a second order derivative of y. So this is if the equation was dy by dx times dy by dx, then it would have been a nonlinear equation, right? This is dy by dx raised to the square, but then right now what we have is d square y by dx square. So this is still linear, right? If the equation was dy by dx whole square, then it would be nonlinear. Okay, fine. What about the sixth equation? Yeah. What about the sixth equation now?
Oh, that's non-linear.
It is nonlinear because you're multiplying product of y with t square y by dx square is what we are multiplying. So this is a nonlinear equation. Yeah. Okay. Fine. Okay. At least we are able to identify what is a. I mean, with these principles, we are able to identify whether it is a linear differential equation or nonlinear differential. This you can apply to any equations that we come across. Okay. I think that is important. Fine. Now, why we are differentiating between linear and nonlinear is if something is linear, we can try directly solve with whatever methods we will discuss. If something is nonlinear, then we have to kind of linearize them and then solve them. Okay. We will see how that needs to be done as we go along. Okay. So now the question is essentially we have this function which is basically given here, which is a function of x, y, and so many d by dx, d square by dx square, and so on equal to 0. Okay, now the idea is now we want to solve for this ordinary differential equation. What do we mean by solve? Solve means that we want to obtain y as a function of x. Okay, so let us say we are given certain domain. The domain is something like this: x equals 0 to x equals L. Okay, and then we would like to we are given certain conditions. Okay, the conditions are I mean, we should be given again, we should be specified these values, either y dy by dx, d square y by dx square, all the way to dn power y by dx to the power n. These values need to be specified at the extremes. That means these values need to be specified either at x equal to 0 or at x equal to L. That means we could choose to specify, let us say, first three values at x equal to 0 and then all remaining values at x equal to L. So we need to specify these values. Once these values are specified at either extremes, essentially altogether, we just need to specify them at one of the extremes. Then we would like to obtain how does our profile y look like. So y as a function of x, of course, at certain discrete points because we are using numerical calculations. So because you're doing discrete calculations, we want to calculate y as a function of at xi. Okay, several other points here. Okay, that is what we try to seek. So this is the solution we are trying to seek when we say solve a particular ODE. Okay. Now again, as we just now said, these n values need to be specified at either of the boundary points that we have. So if all the values are specified at x equal to 0 and none are specified at x equal to L, then we call such a problem as an initial value problem. Okay, initial value problem. That means at x equal to 0 or at t equal to 0, we are specifying all the values that are required, but then we are not specifying anything at the other extreme. That means t equals capital T or x equals L, anything like that we are not specifying. So that's the reason as all the values specified at the initial condition at x equal to 0 or t equal to 0, this is called an initial value problem. Whereas if some values are specified at x equal to 0 and the remaining values are specified at x equals L, then we call such a problem as a boundary value problem. Okay, that means the values of the derivatives or the dependent variables and the dependent variable derivatives, etc., partly are given at one end, partly are given at the other end. This is basically a boundary value problem. Okay. Now, of course, again, we're going to see both how to solve both the initial value problems as well as boundary value problems in this chapter. And further, we are also going to see, we will also focus on methods for the initial value problems more because these are extensively needed in the solution of other types of problems as well, other types of ODEs as well. Okay, so why we say this thing is, even in fact, the boundary value problems can be also solved using the techniques developed for initial value problems. Okay, so we will see, that's why we'll see mostly we will try to focus on how to solve initial value problems, and then we'll also see how boundary value problems can be solved. Okay, now coming to the differential equation, we said we are dealing with an nth order ordinary differential equation. Okay, so that means if we go back to our examples, this is basically a second order ordinary differential equation. This is a second order ODE, and so is this one, and this is the first order ODE, and all these things are first order ODEs, right? Because the highest order that appears is only dy dx or dy dt. So this is the first order ODE, and these are all second order ODEs and so on. So similarly, you can have many other higher order ODEs. Now, again, we will focus on, now it basically is possible to convert an nth order ODE to a set of first order ODEs. Okay, that means if you are given an nth order ODE, we can convert it to n first order ODEs. Okay, that is possible, and because of this possibility, we are going to focus on solution techniques for solving first order ODEs, or so first order ODEs or in first order initial value problems. Okay, now that sounds very nice and simple, because we said, okay, there is an nth order ODE in which there are derivatives of d to the power n y by dx n. But then we just said that now this nth order ODE can be converted to n first order ODEs. As a result, we have to just learn how to solve a first order ODE, and then we just have to apply it to all other, keep solving these n first order ODEs together so that we can obtain the solution. Okay, that is kind of nice. So let's look at an example of, a higher order ODE. Let us look at a third order ODE. So let us consider a function, an ODE, which is f triple prime plus half f double prime equal to 0. Okay, so when I say f triple prime here, we basically are referring to d cube f by, let us say, some d eta cube. Okay, where eta is my independent variable and f is my dependent variable. Okay, similarly, when we say f double prime, we are saying d square f by d eta square. Okay. Okay. Now, okay, this is an ODE that appears that comes in the solution of fluid flow over a flat plate. Okay. So, for example, if you have a plate which is held stationary and there is some fluid that is passing over it with some, some incompressible fluid at some low speed, then the velocity profile that gets generated here will be because of the boundary layer effect. So there is a boundary layer that gets formed. Okay, so I didn't draw the boundary layer properly. So there is a boundary layer that gets formed, and let us say this is the boundary layer height. So we basically a boundary layer gets formed, and then the velocity profile will look something like this, which is basically u is the x velocity, and we are writing this as a function of y. Okay, so u as a function of y. So to obtain this, we call this as a obtained from a similarity solution. This was obtained by Blasius. Okay, this is called the Blasius solution. And in this solution, the fluid flow partial differential equations that we get are systematically reduced to an ODE of this form. Okay, so if you're able to solve this f as a function of eta, then from there you can actually calculate what is u as a function of y, because f just appears to be happens to be u happens to be just a derivative of f. That's all. Okay, so as a result, so this is one common ordinary differential equation that you find in dealing with fluid mechanics. Okay, now this is a third order ODE because the derivative is d cube f by d eta cube. Okay, so then how do we convert this into a set of first order ODEs? So for that reason, so let us now define 1/2 f double prime equal to 0. Let me define a variable that is called g equals f prime. Okay, so I'm defining df by d eta as g, and then let me define h equals g prime. Okay, I've defined another variable h equals g prime. That means my h equals g prime, but g equals f prime. So this is f prime, this is f double prime. Okay, that's what I have. Then I can go back and then look at this equation. F triple prime is basically nothing but h prime, right? It's basically h prime because h is f double prime. So I just need to put another prime here. Plus 1/2 f f double prime is nothing but f double prime is nothing but this is g equals f prime. So this is h, right? Equal to 0. Okay, so this is okay, so this is equation 1, and then this is equation 2, this is equation 3. That means I have equation 1, then I have g prime equals h, or g prime minus h equals 0, and then we have f prime minus g equals 0. Okay, so I have these three equations. Okay, so that means each of them, as you can see, are first order ODEs. Okay, but then only thing is that now they are coupled because this h value needs to be used here, and then g value needs to be used here, and solve. But then, of course, we can solve them together as we proceed in the positive x direction, or positive y direction, or positive eta direction, as we want. And then we can obtain whatever the solution technique we use to solve the first order ODE here can be applied here as well as here. Okay, so in a similar sense, we can convert any higher order ODE to a set of first order ODEs. Okay, fine. Any questions or clarifications till now? Is it clear, this part?
Yes, sir.
Yeah. Any questions? Okay, so then let us now focus on solution methods first for first order initial value problems. Okay, so as we have now motivated ourselves that if we are able to solve a first order ODE as an initial value problem, we can solve nth order ODE, right? Because it's just basically applying the same thing to multiple equations, which we have converted. So we can essentially, in principle, solve them. Okay. Now, what is a first order ODE? So first order ODE can be written as f of x, y, dy dx equals 0. Or another function could be g of t, y, dy dt equal to 0. Okay. So where here again we realize that x is the independent variable, y is the dependent variable. Okay, I think that is easy to see. Similarly, we could have g, t, y, dy dt, where t is the independent variable and then y is the dependent variable. Okay. Sometimes you may also see some people might use h of t x comma dx dt equal to 0, in which t is the independent variable, x is the dependent variable. Okay, so whatever that appears here is going to be the independent variable, right? Okay, so all these things are possible. So this is basically a first order ODE. Now we said this is an initial value problem. So that means at y at x equal to x naught, value would be given to us, right? Y at x equal to x naught equal to y naught is given. Okay. And then we need to calculate what is the value of y at as we go from x equals x naught, x1, x2 all the way to xn. Okay, that means throughout the entire domain length we need to calculate the y values. Okay, that is an initial value problem. Okay. Okay. So okay, that means we are given, let's say this is x equals 0, x equals L. So the y value here is given, which is y naught, and then we need to calculate this at all the different points, okay, because this is initial value problem. So we will obtain certain values here, and then that is how the function is going to look like. Okay, so that's how the function is going to look like. Okay, and essentially the function value will be calculated. All right. So now there are again several methods that are possible, and it is better to rewrite this particular equation that we have obtained in a slightly different way. So instead of writing f of x, y, dy, dx equal to 0, it is convenient to transform this thing x, y, dy, dx equal to 0, and then write it as dy dx equals some little f function of x comma y. Okay, that means we are bringing out x and y outside and then writing it as a different function, and then dy dx is written here. Similarly, when somebody gives you g of t comma y comma dy dt equal to 0, we can write it as dy dt equals g of t comma y. Okay, so this is a more convenient form. Of the ordinary differential equation. Okay, so with this thing, let us look at what are different methods that are available to solve for the ODEs numerically. Okay, so the first one is known as the Taylor series method. Okay, that means we are given. So I will use the dy dx equals f of xy formulation. So it is the same even if you use the other one. So we are given the function dy dx equals f of xy. Okay, and then we are also given what is the y value at some x. Okay, now we need to advance and calculate what is the y value at x plus h. Okay, h is basically your delta x. That means you want to calculate at x plus delta x. Okay, that is what we want to do. As you recall, if we assume that the function f of xy is smooth and its derivatives are well behaved, okay, and they exist. So it should be the other way around. They exist and they are well behaved. With that, we will be able to apply this Taylor series method, which comes directly from its definition. So if I were to expand what is y at x plus h using Taylor series expansion about y of x, then we have y of x plus h times dy by dx at x plus h squared by 2 factorial d square y by dx square at x plus h cube by 3 factorial d cube by dx cube at x and so on, right? That's what we have. Okay. But then, so that means all these derivatives needs to be evaluated at x, and then we can construct what is y at x plus h if we include several of these points. Now, but we know from the given problem was dy, governing equation was dy dx equals f of xy, right? This we already know. That means dy dx, the value at f of xy can be obtained. That means dy dx can be calculated and then substituted here, okay? Because we are given what is y at x equals x naught or x, we know what is this is y naught. So if I substitute for x naught, y naught, I can calculate what is dy dx at that x naught. I'm using x here, which is basically the same as x naught. That is the initial value that we know. Okay, so I can calculate this thing, but then now how do I calculate d square y by dx square, right? So I can include this term, I know this term. How do I calculate the second term? That means I need to calculate what is d square y by dx square. This is nothing but d by dx of dy by dx. This is nothing but d by dx of, from the governing equation, we have dy by dx equals f of xy. So this is nothing but f of x comma y. But then f of x comma y, when you take derivative with respect to x, this is basically a function of both x and y in turn is again a function of x, right? Because y is a function of x. That is what we are trying to solve. So that means d by dx can be expanded in chain rule as partial x of f of xy plus partial y of f of xy times partial y by partial x, right? Because y, how does f change with respect to y is what we are calculating, but then y in turn is a function of x, right? So that's why we are writing d by dx is its change with respect to x is what we are calculating. But then you have the underlying function is a function of both x and y itself is a function of x. Okay, so this is slightly different from what we learned so far. So that means this is going to be partial f by partial x, the first term, and then the second term is going to be partial y by partial x is nothing but this is nothing but f from the given equation. So this is going to be f times partial f by partial y. Okay, so that is d square y by dx square. Okay, and if you want to calculate this at x equal to 0, we can plug in, we can calculate what is partial f partial x, partial f partial y, and then all these things can be calculated at x equal to x naught. Okay, at x naught. Okay, or x, right? Because x naught, y naught are known, so we can, because f is a function of x, y, all these things can be in terms of x and y, for which we can substitute for x equals x naught, y equals y naught, and then calculate this value, and then this can be obtained. Okay, that means we are able to calculate the second value, that is this one also. Then how do we calculate d cube y by dx cube? So essentially we have to apply similar chain rule and then obtain the remaining term. So that means this is going to be d by dx of d square y by dx square. That is nothing but d by dx of d square y by dx square. We just derived this as partial f partial x times f times partial f by partial y. Okay. But again, we realize that d by dx is involves partial f partial x, f partial f partial y, which are functions of both x and y. Okay, and then y is a function of x. So as a result, this should be written as using chain rule partial x of partial f partial x, f partial y, plus partial y of partial f partial x, f partial y, times partial y by partial x. Okay. Now this is going to have a lot more terms. So the first term is dou square f by dou x square, plus the second term is f dou f by dou y. That is going to be, if I operate this thing, it's going to be partial f partial x, partial f partial y, plus if we operate partial x on the second term, that's going to be f times partial square f partial x partial y, plus again here you would get dou by dou x is nothing but f of xy. So the first term is going to be f times dou square f by dou y dou x, plus the second term is going to be, again there are going to be two terms. The first one is going to be f times f, that is f square times dou square f by dou y square, plus the second term is going to be f times, that is this f times, this is going to be partial f partial y, and then there is a partial f partial y already. So this is going to be partial f partial y whole square. Okay. So that means you got 1, 2, 3, 4, 5, 6 terms for d cube y by dx cube. Okay, so we need to evaluate all of these at x equal to x naught and y equal to y naught, and then substitute what is d cube y by dx cube at x naught y naught, and then put it into this formula, right? That is going to basically give us an order h power 4 accurate scheme because we are now substituting for all these things. Okay, so that means we can calculate now what is y of x plus h at um, at essentially x plus h. Okay, using all these values, right? Okay. So that is the Taylor series method. As you can see, this is already kind of a little bit complicated because we have to either analytically or numerically evaluate the derivative. So the Taylor series method is kind of a little bit restricted. So some of the restrictions on this are the calculation of higher order derivatives. Is computationally expensive. Okay. The second thing is that the derivatives of f of xy should be smooth and it should be smooth, right? And well behaved. You know, it should be smooth. It's fine. So only then we'll be able to calculate all these values. Okay. So otherwise, Taylor series method can get very difficult to implement if these are not satisfied. Okay. Difficult to work if these conditions are not satisfied. Okay. However, if these conditions are satisfied by a particular function, then you can essentially extend it to higher order accuracy, right? You could get higher order accuracy and so on. However, later on in the coming up lectures, we will see how to obtain higher order accurate method without making use of higher order derivatives. Okay. So in this right now, we have used higher order derivatives, that is d cube y by dx cube, d square by dx square, and so on. And then we have calculated the yx plus h to a higher order accuracy. But then we will see certain methods which are called multi-step methods in which we don't have to really calculate higher order derivatives to obtain a higher order accurate method. Okay, so that is kind of, that it comes up later. Okay, so we will kind of go for the next method here, which is the method that you already know, and that is your explicit Euler method. Okay, so we have already seen this explicit Euler method, implicit Euler method, and the Crank-Nicholson method, etc., in the context of partial differential equations. Now we are trying to see them in the context of ordinary differential equations. Okay, so in the explicit Euler method, let us say when we are again given this function, this is dy by dx equals f of xi yi. Okay, and we are given what is yi at or we are given what is yi value at xi, and then we need to calculate its value at yi plus 1 equals how much, right? That is yi plus 1 means yi plus delta x, right? Or yx plus delta x or yx plus h. That is what we need to calculate. Okay, so we are given this Euler explicit method. In the Euler explicit method, it is, you can think of it like a is kind of coming from the Taylor series method itself, but then we kind of truncate the Taylor series at the second order accuracy. That means if I were to write what is yi plus 1, we write this as yi plus h times dy by dx at I plus order h square. Okay, that means we can write this as yi plus h times what is dy by dx at I? That is nothing but from the governing equation, this is nothing but f of xi yi plus order h square. Okay, so that is yi plus 1. Now, this is much easier because we don't have to calculate all the derivatives. We just need to calculate what is f function value, whatever is the function that is given as xi, yi, and then just multiply with the delta x that we have, h or delta x, and then calculate the next value. That means we are using the previous value of y and the local slope of the function to calculate the next value of y. Okay, so if I were to draw this graphically, what we have is that, let us say, on the x-axis we have x, the y-axis we have y, and then we have, let us say, some function. This is my y as a function of x. This is what we are supposed to calculate, right? Which is there. But then we are starting off with some xi value, right? Which has a yi value, and these are specified as initial condition. That's why this is an initial value problem. And then what we're doing is that we have to calculate what is yi plus 1. We are adding yi plus h times the f of xi yi, which is nothing but h times the slope of the function. That means we are drawing a local tangent here. So a local tangent would go something like that. Okay, let's say that's approximately the tangent. Okay, so from the tangent, this tangent is nothing but dy dx at x equals xi, which is nothing but f of xi yi. That is coming from the governing equation, dy dx equals f of xi yi. Then we are calculating that, and then we are saying this value. So we are obtaining that at xi plus 1, right? Because we are multiplying this with h. Okay, that is basically adding delta x to xi. Okay, that is x plus h. So essentially, that value is your yi plus 1. Okay, basically that is yi till here plus h times the slope is this height. So those two together is your yi plus 1. Okay, so as you can see, this is of course different from what is the yi plus 1. Actual yi plus 1 is somewhere here. So that is the error we are making in this scheme, which is basically order h square. Okay, so that is your Euler's explicit method. But as you can see, it is very easy to implement. So easy to implement, and progressive values of yi can be obtained by simple substitution. Okay, and coming to the disadvantages, this method is in strong in regions where y values, where y has strong variation, this method would need prohibitively small values of h. Okay, and many a times when there are strong variations of y or strong gradients, then what will happen is that the round of errors in this method kind of grow for certain values of h, and then the solution usually will be unstable. Solution will diverge, okay, for certain class of problems, unless you take very small values of h, which are going to be too small for the case. Okay, as you can see, this method is basically a locally second order accurate. Okay, that means Euler's explicit method is second order accurate for step. That means for each step, that means when we go from xi to xi plus h, it is second order accurate. But then, as you recollect, we want to calculate y at all values of xi plus 1, and so on until xn, right? So we need to integrate this from x0 to xn, okay, to calculate what is the variation of y as a function of x. So when you have integrated for so many steps, the order of accuracy per step is h square, but then you have to do it, you have to keep integrating this every step, and you would do how many such steps? You would do length divided by h, right? Essentially, that is your length divided by your, you basically have to do it n, length divided by n so many times, right? So that is going to be, or when you integrate this n times, right, which is basically nothing but your length divided by the step size h. That is basically going to make it only order h instead of order h square, right? Because this h gets cancelled with this h square. So you have h square by L by h, which is going to give you L times h. So it's only going to be order, it's only going to be first order accurate globally. Okay, so which is not very attractive because we would like to keep at least second order accurate globally as our truncation error for any of these problems. Okay, so then we are out of time. I'm going to stop here, and then unless you have any questions, you can ask me. So tomorrow we will continue with the solution of ODEs. We will look at the other methods, that is implicit Euler method, and then the trapezoidal method, and then as time permits, we will do some example problems, and after that we're going to look at about the stability of these methods and so on. Okay, so ODEs is a slightly longer chapter compared to the other chapters. Okay, fine. Any questions, anybody?
You need to go through once again, sir, please.
Okay. Yeah, sure. No problem. Okay, if you don't have any more questions, then I'm going to stop here.
Sir, I'm wondering how you remember all these equations, sir.
Sorry, say it again.
So how do you remember all these equations? I'm little.
No, I think I've been teaching so many times, so it has become, kind of easy for me. Or, yeah. I think once you learn, you will also be, very at home with these equations soon.
Oh, okay, sir.
Yeah. You just have to work out some problems and then, go through the notes or take notes. That's all. I think you will also be very conversant with these equations. I think there's nothing complicated about them as such.
Yes, sir. Basically, we are trying to find some symmetricity actually.
Sure. Yeah. That's good. Yeah. No, I mean, we are going to look at these things in a similar way. Like, see, these things will repeat, the stability, all these things. But then stability in the context of ODEs, we will do it slightly differently. We will not use the round off error argument, but we will do it slightly differently. We will come to that, later on. Yeah.
Right, sir.
Yeah. Good. Okay. I'm going to stop here, guys. I'll see you guys tomorrow at 4 o'clock.
Yeah, thank you, sir.
Okay. Thank you, guys.
Yes, sir.
Thank you, sir.
Thank you. Bye.